All right. Good morning and good afternoon or good evening, wherever you are in the world right now. We wish you well, and thank you so much for joining us today here for this free webinar here at EIT. Thank you so much. And before anything else, let's do a mic and camera check. Um, Dr. Georgios, are you there?
Yes, I'm here. Hello,
That's
everyone.
great. All right, cool. Yep. So let's do a mic and camera check. Can you see and hear me, Dr. Georges?
I can see you, I can hear you, Marvin.
All right,
Yeah.
and the slides. All right, that's good. I can see as well. And we would like to request our attendees today if you can actually help us check if our cameras or our microphones are working fine. Just kindly set us a thumbs up to confirm that you can actually see, hear, and see the slides on your screens. Thank you so much. Thank you. I can see a lot of thumb ups. Thank you so much. Thank you. All right. How about the others? We have almost 50 attendees here. Hopefully you can see and hear us from your end. Can you share your thumbs up there if you can see, hear, and view the slides on your screens? Good morning from South Africa. Good morning. Okay. Loud and clear. Amazing. Thank you so much for the feedback. All right, cool. All right. From Qatar. Oh, hi, GM. Good morning. Okay. Loud and clear from Uganda. Oh, Uganda. Thank you so much. Okay, I can see lots of thumbs up. So I guess our microphones and cameras are working well. So now let me just let's do a little housekeeping here. So we would like to request everyone to please disable your notifications because we want everyone to have a laser focused attention to this webinar. So the instructions are actually on your screen. And also there will be a short Q&A after the presentation. So Dr. Georges and I will be answering all those inquiries. So you can kindly post your questions in the Q&A section on top of your screens. Okay, so for common questions, FAQs, so for those who have registered, we will be um, sending or you will receive a copy of the recordings, video recordings, as well as the PDF slides to your registered email within the next 2 business days. So just kindly monitor your junk mails. And of course, for those who have stayed until the end of our presentation, we will provide a free digital certificate of attendance, and then a QR code or a link to a short survey will be provided at the end of the session, which you need to complete so that you'll be able to receive the certificate of attendance. Okay, so once completed, we will send your certificate within the next 4 business days. Okay, so for those who have just attended, first timers here at EIT who have attended the free webinars, just a background about ECT, Engineering College of Technology, and of course, Engineering Institute of Technology. So a little background, both specializes in engineering courses. Okay, our programs are industry focused and expert lead programs, and these are being built by global experts, ensuring practical and job ready skills. And of course, our courses for both institutions are globally recognized. So for ECT or Engineering College of Technology offers UK recognized qualifications. For EIT, we provide Australian accredited qualifications, and some of our programs, many of our programs actually, are recognized under Global Engineering Accords, namely Dublin, Sydney, and Washington. Okay, so these programs are being delivered through a unique delivery methodology, which makes use of an innovative, engaging, and practical online learning approach. And of course, personalized student support. So we have a small classes and dedicated support to help students succeed, a global learning community, and of course, an accessible and high quality education as we promise to our students. Okay, so just a disclaimer. The courses and qualifications mentioned in this presentation are offered by separate legal entities operating in different jurisdictions. So one for in Australia and one in United Kingdom. So each entity is subject to its own local regulatory requirements and accreditation standards. So if you are someone who are actually looking for an Australian qualification, you can reach us to our website as seen on your screen. And for those who are interested for UK qualifications, you can also check their website. Okay, thank you so much. And now, without further ado, today's topic would be connecting power electronics to weak grids. This will be presented to us by Dr. Georgios Konstantinou. My apologies, doctor, if I if I mispronounce or something, but correct me if I'm, it's Dr. Georgios Konstantinou, right? He is actually
Yeah.
our yeah, it's actually he's actually our associate professor. He's actually associate professor at the School of Electrical Engineering and Telecommunications. All right. So just a little background. As mentioned, he is an associate professor at School of Electrical Engineering and Communications in UNSW Sydney. Specializes in power electronics and their integrations into modern power systems. His research focuses on multi-level converters, HVDC, MVDC systems, renewable energy integration, real-time digital simulations, and digital twins in power engineering. So he currently leads a real-time digital simulation laboratory and he is an ERC Future Fellow. So now, without further ado, let me give the floor to our presenter, Dr. Georgios Konstantinou. Doctor, you can share your slides now.
Right. Make sure that we can see my slides.
Yeah, I can see it from my end.
And
All
you
good
can
from
hear
my
me
end.
as well. All right, lovely. Well, thank you. It's great to be here. Very happy for having this invitation extended to us at here, the Real-Time Simulations Lab at UNSW Sydney. It's the University of New South Wales. And well, a good opportunity for us to present the work that me and my group, because this is a group effort on connecting and solutions for power electronics in weak grids. So a quick introduction. I think I can skip the first slide because you have already introduced myself and my
Yeah.
work, but I
But
would
if you
like
want
to
to add
mention,
something,
yes?
if you
No,
would like
no,
to add something, yeah, no problem
that's
with that.
perfectly fine. But as I mentioned, the work we're presenting here is a group effort of me and my team, and that is a team of postdocs, PhD students, master students, and some undergraduate projects we are also running. So we are a relatively small research group, but quite active in the area of power electronics and their interfaces to the power system. So a quick introduction to my team and also our laboratory. We are the real-time simulations laboratory at UNSW Sydney, and that is effectively a dual laboratory. We are doing a lot of work that relates to modeling of power electronics and power systems, and of course the connection of the two. But we also have a dedicated power electronics laboratory where we do quite a bit of work on hands-on work on power electronics. That includes hardware configurations, control, and also the experimental validation that goes together with it. So the presentation is called Solutions for Power Electronics in Weak Grids. And I guess the first thing to talk about is weak grids themselves and try to set a bit the premise from an Australian point of view. But hopefully a lot of the things I will mention will translate to some of the experiences in different countries around the world. So the motivation for looking towards weak grids. You will hear me in the presentation talk a bit more, quite a bit about power electronics defined power systems, and just a quick introduction, background on what we mean when we talk about power electronics defined power systems and how this actually translates into weaker grids. So the motivation here starts from a power system that sees higher and higher proportions of renewable energy in the generation mix. But also this expands not only from the generation point of view, but also the way that the system gets built. So higher proportion of power electronics in generation, transmission, distribution, and all the way to loads and the utilization of power. So we see more and more power electronics being connected into the power system. This figure tried to explain this visually. So we have our generation with moving away from the traditional synchronous generation to include now a lot more of solar systems, a lot more of wind systems at large scale connected to the transmission network. The integration of batteries, and we'll talk a bit about the function of the different battery energy storage systems that we would have in our system, but also grid services converters, so things like HVDCs, STATCOMs, power electronics that provide additional services to a network that itself now includes a lot more power electronics. So we're looking forward into hybrid AC and DC systems, and eventually to loads and distributed energy resources. So in Australia, it's particularly interesting because we do have quite a high proportion of distributed energy resources that would be small scale solar PV systems, but also from the load side with modern loads, a lot of discussion recently on data centers and the impact they have on the grid. Data centers are very power electronics driven loads. And looking even further in the future, things like electrolyzers and so on. So this creates a very interesting problem that we need to figure out how to work through in order to get to the reality of the future power system. Now, once we put all of these things together, we realize that the dynamics of the system become a lot more complicated because we do not eliminate previously existing dynamics, things like the slower regulation of the governors and the frequency control and the rotor angle dynamics we used to have from synchronous generation. But on top of that, we add what we see here as subsynchronous resonances that can still happen between synchronous generators, but now happening between synchronous generators and power electronic systems. And also this new area here where inverter-based controls add an additional layer of dynamics. These are much faster dynamics, and this create a whole new layer of problems we need to work through, because the faster things become, the more complex they are for us to analyze, and the more computational resources we need in order to be able to model things appropriately, to understand things appropriately, and also integrate them into a larger system that allows us to study what happens in the bigger network. So a lot of things happening at the same time, adding extra complexity to the network and the way we analyze our system. And this is not a future-looking problem. This is a problem we are experiencing around the world in different cases. So some examples of low-frequency broadband oscillations that we have seen around the world. You can see them happening at low frequencies. The example that we usually have here in Australia looks into the wider area of the state of Victoria, where we have had since 2019, continuing all the way to 2023-24, until this issue was finally resolved, these low frequency oscillations around 7 to 17 hertz, sometimes up to 20 hertz, and this could continue for a few hours at the worst cases, happening mostly because of low system strength. But as you can see, the reasons tend to be quite complicated and very diverse around the world. We could have cases where low system strength would cause oscillations like the ones experienced in North Scotland in the UK, where there's a lot of renewable generation as well, but also through disconnection of AC transmission, controller delays, wind power interfaces, all of them creating issues in the network. From large signal instabilities, here in Australia, we used to talk about the 2016 blackout. There was another event in 2024 that caused not a complete system blackout, but a very big transient and a large signal instability, which led to this 49.35 frequency observed in the Victoria network again. But of course, everything has been overshadowed by the large-scale blackout that Spain and Portugal, the Iberian Peninsula, experienced earlier this year, which has actually given a new motivation for further investigation of all the interactions that we'll be looking today. And there are reports that try to explain this under investigation. We haven't updated that yet, but the way that voltage control, reactive power, and settings of synchronous generators and renewable energy systems have interacted hint on the complexities of the things that we need to be addressing in the future. Now, why this becomes important? It becomes important because for many years we had a very specific system we're working with. It was mostly synchronous generators, and that created three concerns about stability: the blue side of this figure, voltage, frequency, rotor angle. Very well understood dynamics, very well understood problems, but also solutions you could take in order to address these problems. A lot of modeling done in networks around the world in order to minimize or avoid as much as possible these issues of instabilities. Again, we would have them around the world, but phenomena that were relatively well understood. Now, with the inclusion of all the renewables and generally power electronics in the network, we start now seeing two new areas of stability that we need to be a lot more concerned and we need to have better understanding. This includes the resonance stability of the network and the converter-driven stability within converters themselves, and also interactions between converters and the rest of the network. So what we see here is this coupling that we have between converter controllers with the electromechanical dynamics of the machines, but also with the electromagnetic transients of the network. So different time domains, but interactions at a much broader frequency range. And this means that the instabilities we experience in the system is also seeing this wider frequency range. Could be as low as fractions of a hertz, and could be as high as higher than the fundamental frequency, well into the few hundreds of hertz in terms of these oscillations and interactions in the system. Now, from an analysis point of view, traditionally system strength has been quantified through fault current level calculations. So it was a relatively straightforward procedure of looking at your network, trying to understand the states of the network, heavy loading conditions, low loading conditions, how much synchronous generation you would have available at a particular point in time, the interconnections, the lines that you have available, and then calculating the fault levels at the different buses. Now, with the transition to more and more inverter-based resources, this no longer tells the whole story about how strong the system is. So we're looking into trying to understand whether we need to redefine system strength, whether we need to understand system strength from a different point of view, and what metrics we might want to use in order to identify a strong grid or a weak grid. At this stage, there's quite a bit of work being done. Definitions are still a bit fluid, not fully set, but the main the power systems operators around the world seem to have at the moment a focus towards this stability of the voltage waveform as a general description. And then we need to kind of see what that means in the bigger picture. So locally in Australia, we use the definition of system strength from what AIMO initially defined in 2020, which is this ability of the power system to maintain and control the voltage waveform at any given location. Now, with the explanations that this needs to happen both under steady state operation and also following disturbances. So where the fault current level might give you some indications of what to expect, but the reality is that we need to understand what could impact the voltage waveform at a particular location, and how well can we regulate under steady state and also during transients this voltage waveform. So all the events that we mentioned earlier and the impact that they have in the operation of the system kind of makes us rethink how good these formulations are and these explanations for system strength are in telling us what happens in a system with a lot of power electronics. Now, some examples of short circuit ratio and the traditional definitions, even with power electronics converters, looked at the ratio of what we call the short circuit power following fault calculations at a specific location relative to the rated capacity of the generator that's connected at this particular point of view. So this was a relatively straightforward definition because when we had even a single plant connect to the grid, we could very easily look at the aggregate Thevenin equivalent. So you can see we translate this whole power system into an equivalent network here, high voltage, medium voltage, transmission lines, system impedance up to the point of connection, and typically a small impedance from this point of connection back to the equivalent network would generally guide us towards a strong grid, and a relatively large impedance would give us, of course, less control of the voltage waveform, a lot more local impact in the voltage waveform at the points of connection of any new generator, and that would hint towards a weaker grid. But the more and more renewables we connect, the more and more inverter-based resources we connect into the system, these definitions become not very useful in telling the whole story. There were attempts when still the proportion levels of inverter-based resource in the system were much smaller to try to redefine this short circuit ratio, to try to look at what were defined as the equivalent or composite or weighted short circuit ratios. So trying to redefine the way that the injections from inverter-based resources to the rest of the network would take place. But again, with a focus to this specific short circuit power at a particular location, and then the definitions based on inverter-based resources. Now, as I mentioned, these are very good indicators when we have a system that has a lot of synchronous generation in it, and a lot of systems still maintain a lot of synchronous generators in them. But in a lot of networks where we are transitioning to more and more renewables, we find ourselves into a system that, as we described earlier, a lot of the generation in the network no longer comes from synchronous generation. It comes from inverters, and this adds to the complexity of the analysis and takes away from these fundamental definitions that we're using for a long time. Why is that? This is because, first of all, IBRs have different synchronization modes. There is a control element, there is a measurement element, and there is an electronics element into the operation of power electronics converters. So the synchronization modes we used to have with synchronous generators do not necessarily directly apply to a modern system with a lot of inverter-based resources. The additional things we need to consider is that since we have control functions and the system becomes non-linear, it also exhibits very complex responses across the frequency range. So a very simple value of an equivalent impedance no longer describes everything that we expect to see from a power electronics converter, because its behavior changes at low frequencies, at frequencies around the fundamental 50 Hertz, and at frequencies that are much higher because of the way the converter operates, obviously. Also, our power electronics are current limited. We cannot get the very high currents that we would get from a synchronous generator in the event of a fault. And because they are current limited, the fault contribution they have, the amount of current that comes out of them during a fault, is much lower. So if we look at the previous definitions, we would end up with very, very low fault current levels. And that kind of tells us that just simply using fault current doesn't necessarily tell us the whole story about the system, the strength of a system at a particular location. This again creates all these concerns that we mentioned here. We have to worry about instabilities that appear when we have a lot of the grid following converters, which is the vast majority of large scale and small scale systems that we have connected in our network today. If we are using overcurrent in order to do the protection from things that we have downstream from a feeder, for example. Since we are current limited, the protection requirements fundamentally shift away from overcurrent because we can no longer supply very high fault currents very quickly. Voltage regulation and control becomes a bigger issue. That's what also the blackout in Spain exhibited. The system recovery becomes different because we do have different control modes for our power electronics converters. Oscillations might appear that might be poorly damped, also because of interactions with power electronics converters, and small signal instabilities, converters fighting with converters that are within the same farm or with systems relatively near to their location also create additional problems. So transition in the system creates problems, and these problems tend to become bigger and bigger and more complex to address as we put more and more of these systems in our network. Now, to further explain why this becomes a completely different level of complexities that we have to work with in our system, when we're analyzing a traditional power system with a few, even in the hundreds, synchronous generators, we had a network that could translate into a small number of nodes. So we could use network reduction methods and end up with something that might not be very big, but still give us the fundamental behavior of the network. And in the case of Australia, because we had interconnections between the states, so one transmission line or maybe two transmission lines going through borders between states, this allowed us to do analysis at an individual state level and then make sure that things are relatively stable at a particular level and move forward to the next state. Now, once we put hundreds of inverters for solar farms, wind farms, battery energy storage systems, loads, and so on, these models become higher order. They are very difficult to generalize. They are very difficult to substitute. And if we start generalizing and substituting, we maybe start losing details that is necessary for the understanding of the system to truly see what will be happening in the system. Also, when we have a synchronous generator-driven network, analysis methods that depend on RMS values, so phasor level methods, give us a very good indication of what's happening in the network. But in a power electronics environment with a lot more IBRs, we need to have models down to the level of EMT. That requires a completely different level of modeling, completely or a lot more additional information in order to create these models properly. And as I also say here, very difficult to get white box models for all these new types of generation. For synchronous generators, typically we have very standardized ways of controlling them. Their governors, their exciters are well defined, and generic models give very good representations. This is not the case in case of solar inverters, wind farms, and battery energy storage systems. So this takes me to the next bullet point, availability of models. In most cases with IBRs, we might have to work with black box models. We might have to work with compiled DLLs of the control functions, which does not give us visibility on the way things are happening on the background. Maybe some stuff can happen with hardware in the loop integration and what we call here gray boxes. But again, this is a much more complex system, and we no longer have full visibility into the details of the components that we are modeling in a much more complex network, as we saw earlier. We have not reached the level of standardization that we have with synchronous generators, different control choices, different hardware, different power plant controllers and their implementations. All of them compound to make everything more and more complex. Then when we look at the implementations, we have multiple options for multiple different elements of the control of the inverters. So some manufacturers might choose power limiters, some might use current limiters. How are these implemented? Not particularly clear and not very visible yet to everyone analyzing the network. We also will have some sort of synchronization challenges that might appear, which we need to understand better. And finally, when we look into IBRs, some hardware in the loop solutions are available, but to do that at large scale with the hundreds of renewable energy plants at detail becomes very complicated. So in summary, what we get out of this slide would be that things have gotten more complex, more in terms of units that we need to analyze, and more in the level of order that we need to have in our models and our systems in order to be able to understand these power systems that are including more and more inverter-based resources. So a substantially more complex problem that requires also new rethinking how we approach this. So if we look at, again, the dynamics and the different transients that we need to work with in a synchronous generator defined power system, our traditional power system, the time separation that we have allows us to split the time analysis that we do and focus on an individual level of interest. In the case of a power electronics defined network, this is no longer possible. We have overlapping timescales, dynamics that interact with each other, and this makes, again, the simplifications a lot more complex and a lot more difficult to achieve. Then we need to consider the different problems we have in terms of stability. We have large signal issues, we have small signal issues, and in the current approaches, because these were not particularly tied in the case of the previous power system, we're using different system strength metrics in order to identify large signal strength and small signal strength. So in the end, the question is, if we have a network that is driven by power electronics, that is defined by power electronics, that's defined by solar, wind, batteries, and loads and networks that have a lot more power electronics in them, how can we combine the two? And how can we get appropriate metrics that tell us information that relates also to the operation of power electronics converters? This is an ongoing problem. I'm not going to say I have very, very good answers. We have some proposals from different research institutes and universities around the world. Some of them are being implemented by market and power system operators, but the way that this is done is still at the very early stages across the power system. In the end, though, we need to understand that we cannot really separate the different elements. We cannot separate inertia, system strength, and the system impedance, looking back at that equivalent network. And all of them need to be considered simultaneously in order to make sure that we have a safe and secure operation of the network. So we need to make sure that whatever we use to define a strong grid or a weak grid captures fault level, captures inertia, and captures elements of the impedance at a particular point in the network and whatever connects to that point of the network, in order to make sure that we avoid or have a stable system following faults, following frequency events, and also avoiding these oscillations and interactions between different elements of the system. So again, we don't expect these things to go away. We expect these things to get worse and worse because we do have a lot of synchronous generation that is expected to leave the network. In Australia, there is a plan for retiring synchronous generators and coal-fired power stations over the next, I want to say 7-8 years. Now, how much of this will actually take place, still a question, especially because of system security aspects. But the reality is that we will have a lot of these coal-fired power stations retiring in the near to medium future, and we need to prepare ourselves for this kind of issues. So we end up with a network that is effectively now defined from power electronics converters, which means that a lot of the functions that we used to get from synchronous generators needs to come some way, one way or another, from inverter-based resources. So we need to be able to form the grid, which creates all this discussion about grid forming converters that I will spend the rest of this presentation talking about. And as I mentioned here, how do we get this responsible grid forming design for our inverters in order to be able to address all these issues that we have been introducing for the first part of the presentation. As you can see from this slide, the grid forming control, specifications, better understanding, white papers, details of implementations are becoming more and more common, coming out of different power system operators. Back in 2020, you would find the first examples of discussion that goes into power system operation with this grid forming control. But as we go towards 2021, 22, 23, 24, and now 2025, there is a lot more work coming out from different power system operators trying to understand power systems with power electronics in them, but also try to define the requirements and define the expectations we have from a system with more and more inverter-based resources. So if we try to understand grid forming control, we need to see how we try to give a general definition of this grid forming control. And in our case, working with the initial definition from the US from NERC, we're looking at, I'm mentioning that because a very similar definition is also adopted here in Australia from AIMO, is a control that allows us to maintain, right here, an internal voltage phasor, so linking that to the voltage waveform stability we saw earlier for a strong or weak grid, that is constant or nearly constant in the subtransient or transient time frame. Now, once we see this, we need to try to understand what each of these words mean. So when we look at the voltage phasor, we have three effectively elements that we need to consider. The first one is the amplitude of the voltage, that E in the E sine omega t plus phi, a very typical voltage phasor, which corresponds to how does our power electronic converter behave under voltage sags and swells? What happens when the voltage goes down? What happens when the voltage goes up at the point where it connects to? The next thing we care about is the frequency. So that omega in the sine omega t plus phi. That omega effectively correlates to response of converters under frequency excursion. What happens if frequency goes down? What happens if frequency goes up? And how do I get my converter to achieve its goal of grid forming under these circumstances? Finally, and the one that seems to be the most interesting point for analyzing in the recent years, this phi. How do we maintain this constant phasor, and what do we do for the phasor generated by a power electronics converter when we have a change in the angle? So how does the converter respond during phase jumps? So we see that all the events that we expect to have in the network effectively translate into one of these three cases or combinations of these three cases for our converters. So voltage dropping or increasing, frequency dropping or increasing, phase jumping forward or jumping backwards, changing this network value. So in order to avoid, in order to be able to generate this grid forming control, we are looking at effectively an internal way of synchronizing converters to the network. That's what we refer to as a self-synchronizing mechanism, which most commonly, so when you hear of grid forming control, in the majority of cases refers to a synchronization through a power loop. And when we look at the synchronization through a power loop, we go back to very basic definitions that have been around for a long, long time when we operated things as UPSs, where we had a very strong definition of the voltage and the frequency. But when this happens within a network, we need to see how we can better share this power with everything else that exists in the network, which means we need to start looking at introducing things like a droop control that allows us maybe to do some power sharing between the converters, or replicating some of the responses of synchronous machines within the control structure of the power electronic converter. This means different ways of doing that: synchroverters, virtual synchronous machines, VSGs, virtual synchronous generators, matching control, and so on, or an internal time-based synchronization method based on virtual oscillator control. So all of them effectively end up to the same common point, generating an internal reference for the phasor, this voltage reference here, and this internal angle in the grid forming converter that allows you to effectively regulate what happens as you connect this inverter to the rest of the network. So if we look at what we have in order to achieve this self-synchronization control, we go from what was a synchronous generator to power electronics converters. So we have a fundamental shift in the structure because we are going from what is a passive element that is physics-based, the electromagnetic principles of a synchronous generator, to what is a control-based system defined by power semiconductors. So we are the ones who switch the converter, and we have switching elements inside the converter in order to regulate this current. This allows us for very high controllability, very high response times. So we do have a very good armory of tools in order to respond to what's happening in the network. But at the same time, we tend to be limited to the amount of power that we have available. And as I mentioned earlier, we are limited to how much current we can get out of these systems, because high current through power electronic converters, usually after a few seconds, means smoke coming out of these converters. So a couple of ways of thinking how we put together the system. One way would be our synchronous generator being that big lorry driving down the highway, doing a lot of carrying, but also very slow to respond, versus a fast car. So we can regulate very quickly, get it to respond very quickly, but also not to the capacity in terms of movement that we can get out of a compared to a truck. Or another way, a cooking analogy to think about it, synchronous generator gives us a pot that cooks slowly. A grid forming converter gives us a microwave, very easy to control, very quick to respond. But again, getting the two to get us a delicious dinner, which is what we want to get in terms of a stable system, becomes a different discussion. As I mentioned earlier, this is not a straightforward discussion only about inverters, because we need to consider what sits behind the inverters. And the reality is that if everything was batteries, things might be a bit simpler because they are a lot more better defined in terms of energy that they have sitting on the DC side compared to everything else. But once we move away from batteries and HVDC systems, things like wind, solar, fuel cells, loads themselves, hydrogen generation becomes a lot more complex and a lot more limited in what we can do at the DC side of these systems in order to maintain stability with the network and internally to these elements of the converters. And the extra complexity we need to work with is that our power electronic systems need to be current limited. One of the things I mentioned earlier is that they cannot handle high amounts of overcurrent going through them. So we need to limit this current, and this changes the way that they behave when they connect to the grid and when we have faults that we need to respond when they connect to the grid. So as an example here from this excellent report from connecting more renewables into the grid, you can see the differences with a synchronous generator. You have a fault, synchronous generator behaves with its transient and subtransient reactance that tends to be quite small. That gives us a very high value for the fault current, and this fault current defines the transient response of this generator. In a current limited inverter, you can see if we do have this ride-through capability, still we are able to generate current, but this current is nowhere near the amount of current we would be getting from a synchronous generator, which creates all these additional issues and problems for the interface and for a power system which has more and more power electronics connected to it. So if we look at it from the point of view of power electronics control, if we are to limit this current, we have a couple of options to do that. We have what we call a direct current limiter, where we're trying to directly limit the current that comes out of a grid forming converter through directly affecting the control structures that we have inside the converter. We can do it in a secondary way by what we call voltage limiters. So we are trying to limit the delta V across this value here, which includes the impedance of the converter, but also elements related to the grid and the filter of each individual converter. or with a direct action on the overall impedance that the converter thinks it's seeing, what we call a virtual impedance, a modification of this value here at the output of the grid forming converter. All this sound good, as in we can achieve these goals, but the biggest issue we have is the moment we start trying to limit the fault current we get out of the converters, we have a fundamental conflict between the objectives of the grid forming control, which was this self-synchronization and the ability to maintain this internal phasor of the voltage, with us limiting the current. So we need to better understand what is happening with these converters and how the current limiting methods in grid forming converters affect the converters themselves and the system as a whole. So when we look at the current limiters directly, so the ones that allow us to directly limit the current, we have a few options here. Let's go quickly through this. We have the option of, as you can see, limiting the current directly. So whatever value we have, we instantaneously limit it to the nearest value. We can have a variation that allows us to proportionally limit it to P and Q values. So we can get on the D axis and Q axis, which allows us to control active and reactive power differently than the instantaneous current limiter. And we have the option I mentioned earlier of the virtual impedance that adds this delta VQ here, that allows us to act on the voltage controller and limit the amount of current that we get out of the converter. The reality is that when this happens, we do have a direct impact on the synchronization structure and the synchronization behavior of a grid forming converter. And that is because what was an ideal P delta curve, which you should be familiar from a synchronous generator behavior, changes substantially. So the current limited grid forming converter behaves as this red line, and this red line also depends on the voltage that it sees at its terminals because of the faults that exist in the network. And this, as you can imagine, complicates the analysis that we have and the level of complexities that we need to address in this system. So this goes back to some of the research that we are doing ourselves with our research group here, that allows us to look at different options on how we can control and how we can regulate this self-synchronization aspect of grid forming converters. Some ideas that we have put forward here, I'm trying to summarize them quickly. One of them looks at moving the synchronization loop from the outer part here, directly acting on the voltage and the angle, inside the current control structure and after the current limiter. So in what we call the current synchronization loop, it avoids some of the synchronization challenges that we have when we are limited to what we can do from the outer loop because of this current limiter that exists in the grid forming converter. Another way to think about it here, in my screen.
My apologies. Yeah, I think my apologies. Would you be able to share your slide again, sir? I'm so sorry.
Yeah, it's all right. Can you see them now?
I cannot see it from my end. Oh yeah, there you go. There you go. Thank you.
Okay. So get this guy back. Yeah, I was thinking about the variation, or if you want, trying to effectively understanding that the response of the converters and the behavior that we have depends on what component acts on the high frequency components of it. Is that back on? Yes.
Yes,
what acts on the high frequency components of it and what acts on the lower frequency. So we can achieve that with different ways, and this bandwise power synchronization loop is one example of this way, where you can see that the high frequency component acts directly unfiltered, whereas the low pass component is the one that is getting current limited, and power limited, and that allows us to have a better response at higher frequency behaviors and different response at the lower frequency behaviors, which gives us a much better operation for this synchronization loop. And finally, a third way of thinking about it would be adding frequency aspects into this power synchronization loop. Our initial idea here was with the inclusion of a PLL. The PLL no longer synchronizes the converter to the grid. We still have a self-synchronized converter, but this additional information we have from the frequency loop adds this damping power that we can add to the system, and that improves the synchronization stability under current limited conditions and fault current limits. And with all these different approaches, I think I'll close this presentation briefly with some of the practical examples of where we try to implement some of these things, not with the fully research level applications, but at the very basic grid forming operation of the system. The example I'm going to use is a project we've been involved with in Broken Hill. For those of you who are not familiar with Australian geography, I will skip to the next slide. This is a map of the east coast of Australia. We're based here in Sydney. Melbourne is down here in the south. And approximately 1,200 kilometers west from Sydney is the mining town of Broken Hill. And as you can see from this map, it sits at the very end of a very long transmission line. And more interestingly, all the oscillation issues that I was mentioning earlier in the presentation about Victoria in Australia are happening in this area here. So we have a part of the network that experiences oscillations, out of which a single transmission line goes to this remote location, where we also have a solar farm and a wind farm that we need to account for. So this creates a very complex environment because it's a very weak grid. All the aspects of weak grid concerns that I mentioned at the very beginning of this presentation actually appear here. And in order for us to make sure that the system maintains stable operation, we need to consider this grid forming operation of any system we connect at that particular location. So geography out of the way, electrically, we have to deal with that very long remote transmission line, a 52 megawatt solar PV system, a 200 megawatt wind farm, and that is based on type 3 double fan induction generator wind turbines. And now the inclusion of this 50 megawatt battery that we need to get into a specific control self-synchronization manner that will allow us to maintain system stability in that particular area. So electrically, this is a view of the network. We have the rest of the network with all the weakness and instabilities here, 266 kilometers of the transmission line to our solar farm, wind farm, battery, and of course the loads that exist there. Broken Hill is a mining town, together with two SVCs that are used for additional voltage stability in that particular location. So implementing grid forming structures, so taking away the using the external grid as a synchronization and looking into all these different approaches for self-synchronizing the converter of the battery into the network. What we can observe here is, first of all, if we were to choose a typical control of this system based on what was traditional grid following control, the same way that every other system was controlled and has been controlled around the world, we see that in the case of oscillations, the battery, when we connect the battery in a traditional mode, the oscillations not only do not go away, but they become worse and worse and worse, and eventually the system can become unstable under certain conditions. In our case, when we try to add the same battery, same specification, same everything, but with a self-synchronizing loop, we see that eventually we are able to dump down all the oscillations that we had experiencing in that particular part of the network. And after a few seconds, we can get into a quite steady voltage waveform. So not only we didn't add to the issues experienced in that area, but we're able to address quite a few of these issues and eliminate some of the oscillations. When we see the same thing, but when a fault occurs, so we have a fault happening here with no battery, a grid following battery, and a grid forming battery, we can see that following different faults in the network, this is only one example of faults we applied here, with no battery or with a typical battery energy storage system, we experience oscillations. Of course, these are not oscillations that we would want to see in the system, and they do not really go away. It's just a simulation example. And the system fails to recover in its previous steady state. In the case of the grid forming battery, we can see that we're able to recover from this fault and maintain the system to where we would like that to be. So we get all these benefits of a stable or a more stable system in a very remote location because of the connection of a grid forming battery. We do get some additional benefits when we look at traditional definitions of system strength. We're looking at higher short circuit capacity and increase in the fault current if we were to do traditional fault current calculations. And you can see here an increase of around 32% in the case of capacity of short circuit current we can get at a particular location. That's short circuit capacity, so fault level at this particular location. In the case of faults, again at very high penetrations, we can see that this we have events where with no battery or with a grid following battery, the system will become unstable, but the inclusion of a grid forming energy storage system allows us to maintain a stable network and oscillations dying down, frequency or voltage oscillations that we might experience under different faults. As an extra benefit, if we are to explore adding more and more inverter-based resource in that particular location, we can see that in the case of a grid-forming battery, we are able to add extra. So we have the option, not that we would like to do it in these particular conditions, but we do have the option of increasing the amount of renewables we can add, or inverter-based resources, not only renewables, in the lower voltage bus, so the medium voltage 22 kilovolt bus, or in the higher voltage 220 kilovolt bus. So you can see that this takes us to a capacity of 252 megawatts that we can accommodate in that particular area without any stability issues. So we see that inclusion of grid forming converters in very weak grids gives us these benefits because we are able to eliminate oscillations that might exist or we might be at risk of experiencing. They enhance system strength and they also increase hosting capacity of renewable generation. And these are very interesting conclusions because we do expect to see more weakness in networks. Australia is experiencing that already. We probably will start seeing it around the world in different areas. Some might take a while, some might be very, very far away. But in some parts of the world, these are things that we need to consider sooner or later. And of course, when we consider sizing of system and the way that we implement these controllers, we need to do these studies in order to determine what level of support we get out of grid forming converters for these challenging conditions. If anyone is interested in this work, we have published quite a bit in this particular area, from grid forming control to stability analysis to operation mitigation of oscillations with grid forming converters. So I have included the slide with some of our research papers for those of you that want to read a bit more. And this brings me to the end of my presentation. So, Arvin, if you have any questions, I think that would be a good time to
Yeah,
address them.
thank you.
Otherwise,
Exactly. Thank you
thank
so
you for
much, Dr.
taking.
Georgios. Yep. So while we are actually waiting for those questions, let me just share my screen. Just a sec. Just a sec. All right. Thank you so much again, Dr. Georgios. So, yep, for those who are interested, in knowing what courses are covering this topic. So basically, as you can see on your screens, we have the professional certificate courses. We have professional certificate courses in circuit breakers, switchgears, and power transformers. We also have the professional certificate of competency in power distribution. We also offer the professional certificate course in electrical power system protection, the undergraduate certificate course in electrical and electronics engineering. We also have the graduate certificate course in mechatronics, and of course, the graduate certificate course in power system analysis and design. So those who are interested to join us for our future or upcoming courses, we do have the schedules on the screens. So basically, by January 13, we will have the Advanced Diploma in Industrial Data Communication Networking and IT, and Advanced Diploma of Robotics and Mechatronics Engineering. So if you are interested, please feel free to visit us on our website or contact us. You can also book a call to our friendly course advisor, and we'll be happy to assist you. Okay. So yep. Now let's proceed to short Q&A. Just a very short one, Dr. Georges. So let me see if we have questions here. Sec. Okay, yeah. So the slides will be provided to those who have registered to the event, to the webinar. Okay. So yep. Any questions? All right. I guess yep. Let me see if there are any questions. Thank you so much, Giuseppe. We have Cedric. Cedric, can you please chat type in your, yeah. Are any of these courses online? So yes, basically there are these are online courses. So we have question from Antonio here. Dr. Georges, how would you balance voltages from a PV installation to MV substation? This is actually from Antonio, one of our attendees.
I'm not really sure how related is this question to the presentation. I'm not sure which voltages you would like to balance.
Okay.
So if you have unbalanced voltages,
Mm-hmm.
that from the point of view of
Mm-hmm.
so okay, going back to what I was presenting earlier, I don't know if this question is related to my presentation or not, but grid forming control is very useful in weak grids, but at the same time, it doesn't work very well in strong grids. So when you have a very strong point of connection, even if the voltages are unbalanced at that point of connection, the grid forming control does not necessarily work very well because you have effectively two voltage sources trying to control the very same voltage location. If you have unbalances in your system from a PV point of view, there are standards, there are controllers that allow you to change the amount of current and reactive current or active current that you can inject for each phase in order to try to improve the unbalance that you have in your network. But given it's a PV system, you're relatively limited to what the standards allow you to do with this injection. So I think the unbalances, if they're coming from the network, need to be addressed at a different level than, I guess, simply trying your PV system to fix them. I don't know if that answers the question though.
Yeah, hopefully it answered your question, Antonio. So yeah, due to we only have limited time here. Thank you so much, Dr. Georgios, for sharing this very insightful topic today. And we would like to thank everyone as well who have attended and spared their time joining us today. So for those who are asking, here's actually the link, and of course the QR code that you can scan so that you'll be able to get your certificate of attendance. Okay, so basically you need to fill out a form, and then after that we will send you your certificate of attendance for today's webinar. Again, thank you so much, everyone. Thank you. thank you, Dr. Georgios, for for being here today and for sharing us this information, this topic. Thank you so much, and hope to see you, everyone, in our future webinars. Thank you.
Thank you. Thanks for the invitation again.